Hypothesis testing. So hypothesis testing refers to a set of techniques of inferential statistics. It's only one set, not all of them. It compares measurements, so mean, variance, or correlation, to determine if the differences between these measurements are statistically significant. So a common hypothesis is to test whether a mean from a sample equals to the mean of the population. And it's usually going to be set up this way over here. We will assume that the mean we're getting from the sample equals to the population, and we call this X bar. Oops, we call this X bar, we call this mu. Mu is the average of the population, mean of the population, X bar, the mean of the sample. And depending on the context, usually you're going to assume that the sample mean equals the population mean. But for a variety of reasons, you may want to test that hypothesis. Maybe that hypothesis was suggested, but never really tested empirically. So, and maybe there's some new evidence that suggests that the sample mean is not equals to, or the population mean, or there's a new population mean rather. And then we want us to test that. So the alternative hypothesis is that the mean that we find from the sample that we're going to study is not equal to the established known population mean. And hypothesis testing is based on assumptions about the population distribution of the relevant variables and the calculation of p-values or probability values. And we're going to delve into this right now. So the normal distribution. For hypothesis testing, we need to know the probability distribution or the probability distribution function of the data. And the probability distribution function is a smoothed out frequency distribution, like we saw with the histogram. And as a frequency distribution, it depicts how much of the instances of a specific variable. And I kind of emphasize here instances of a specific variable and how they fall below, at, and above the mean. So all around the mean. So what we're going to have is in all these kinds of probability distributions, histogram or PDFs like this, in the x-axis, we're going to have the value of the variable. Once again, one variable at a time. So the value is here. The mean here is just generalized, normalized, just mean, whatever the mean is, 3.5, 5 million, or 6 billion, or whatever it is here. And on the y-axis, we have the frequency of instances, so the amount of individuals or data in it here. So the higher the value, the more instances, the lower the value, the less instances. In the probability distribution function, we have kind of probability, standardized probability numbers. But in the frequency distribution, or as we see and as we have seen, we're going to have just the actual number of whatever sample you're using. So the normal distribution curve is an idealized type of probability distribution. We often assume our sample and population approximate our normal distribution, but this needs to be checked. And sometimes we cannot assume this because we know that the domain we're studying, the kind of variables we're studying are not normally distributed. So the normal distribution is very useful. A lot of measurements, a lot of variables in the world, a lot of processes follow this distribution, but a lot of them do not. So we need to know the kind of information, the kind of data, the kind of processes and things we're dealing with. So in normal distributions, if you have a normal distribution, 68% of the data, or 68% of the data instances, the individuals, are within one standard deviation of the mean, all the values of the individuals, whatever it is that one variable you're measuring. And 95% are within 2 standard deviations of the mean, and 99.7% are within 3 standard deviations of the mean. So these are the generalized measures for any distribution that follows a normal distribution. Whatever you're talking about, birth weight, birth height, any kind of variable, so, okay? So let's talk, before we go into a specific example to clarify these, let's talk about the standard score. The z-score or standard score is the count of standard deviations from the mean in a normal distribution. So it is used to facilitate calculation of how far a value is away from the mean. So usually we're dealing with a particular variable the mean is not going to be 0. It's going to be 3.7 or 12.3% or whatever it is. But the z-score kind of normalizes whatever value you have, the z-score formula and the z-score calculation, which we're going to examine. It standardizes the value so that the mean can sit at the center here. It's kind of like 0. And we can calculate the values in terms of standard deviations from the mean. So it just follows pretty much kind of once again, the count of standard deviations from the mean. So a z-score of 1 means 1 standard deviation of the mean. A z-score of 1.5 means 1.5 standard deviations of the mean, and the same goes on the other direction. In minus 1.5, minus 1.5, 1.5 over here. Z-score means minus 1.5 standard deviations from the mean. That is minus 1.5 standard deviations below the mean, and so on. So next, I'm going to stop here and we're going to examine this birth weight example to better understand these concepts.